So I think we are ready to start. The second press conference of the day is on flood disasters, impacts, and forecasting. And we have Giuliano Di Baldassari is a senior lecturer at the UNESCO Institute for Water Education in the Netherlands, and Peter Burek, who is a researcher for the European Commission at the Joint Research Center Water Resources Unit in Italy. Thank you. You can start.
Good morning, everyone. I'd like to give a short presentation to introduce the topic of the day, which is on flood disasters, impacts, and forecasting. I'll give a short presentation looking at flood trends and population dynamics. This will be a very brief overview, and what I would like to show is how population change have exacerbated the impacts of floods in many parts of the world. I will make some specific examples of that by referring to continental scale studies as well as local studies. So first of all, I would like to just to make clear that when I speak about floodplains, I mean the areas that are periodically inundated from a river, from a lake, or from a sea. So this is the definition of floodplains. So are areas that are prone to floods, which can be every year, or can be every 10 years, or every 100 years. So these floodplains are one of the most valuable ecosystems for supporting biodiversity and providing services to the environment. However, at the same time, floodplains are also areas that where economic development is facilitated because of the flat area, because they are sort of roads. And this is why, since the first civilizations, humans tend to settle in floodplains. It is estimated that currently 1 billion people live in flood-prone areas. And this was the case since the first civilizations, like the Egyptians that developed in the fertile floodplain of the River Nile, the Sumeri civilizations developing between the Tigris and the Euphrates flood-prone areas. Now, the problem is that we have many advantages from floodplain, but then also we get flood disasters. And this is becoming more and more a serious issue as flood disasters currently affect more than 100 million people per year. And when we look at data, flood losses, flood fatalities, we can see that flood damages are increasing in many parts of the world. This is, for instance, the case of flood fatalities in Africa that have increased by a factor of 10 over the past 50 years. And if we look at the location of deadly floods in Africa, we can see that deadly floods mainly occurred where the population has grown more. So there is a tendency of many cities to develop and to grow in flood-prone areas as they offer favorable conditions for economic development. So we have more and more people that are living in floodplain, and this is driven on the one hand by the fact that we have a growing population, but on the other hand also by the fact that there is a growing urban population, which is driven by economic development. Now, I want to give also a very specific example of this, which is the flooding of the city of Jimani in the Dominican Republic that occurred in May 2004. This flooding killed more than 100 million people. Now, if we look at this map of the city of Jimani, we can see how the city developed starting from the 60s. 1967 is the area of the city as it was in 1967, and then the orange is the city in 1984, and then the final expansion in 2000 in red. Now, if we look at the flood extent, we can see that part of the city was affected by this flood because the flood occurred in 2004. But if the same flood had occurred in 1967, and the city was the green area, no one would have been affected. So this is just one of the many examples that we can find by looking at historical floods, showing how inappropriate urban development in flood-prone areas have exacerbated flood fatalities. Now, what can we do as earth scientists, being at the EGU, I want to leave with a positive message. And there will be the second presentation, which is about forecasting. So what I would like to stress is that nowadays we have the possibility to make models, mathematical models, able to make predictions of river hydraulics and floodplain inundation, and then use the results of these models to map areas that are prone to floods. And therefore, when we plan land use, when we plan the urban expansions, we can use this as a reference to avoid additional human settlements in flood-prone area. It must be said that in some countries there is not a formal land use and urban planning, but still the publication of results of floodplain models can be a way to raise awareness of people living in the floodplain and discourage additional human settlements in flood-prone area. Thank you very much.
Good morning. Thank you, Giuliano. You gave already a good introduction into my topic, why working on floods is necessary, and it becomes even, with your introduction and with your message, more necessary for the next few years and decades. So that picture shows a map of where flood occurs in the last 25 years, and you can see that's almost the same, or it's the same map as population density. So almost, in the last 10 years, almost 100,000 people died because of floods or flood-related issues. So on the other side, floods are also transnational. Floods don't respect any borders. A good forecast, on the other side, could help local authorities or even international organizations to have some time to prepare and to react before the flood or to prepare for the flood. And that may turn a natural hazard maybe not into a disaster, but into something manageable. Before I go global, I want to mention our European flood awareness system. We run a pan-European flood system since 2003, operationally twice a day, and we distribute our results, our forecasts, to the national hydrological centers in Europe as a complementary information. Now you can ask for sure, why another flood forecasting center? Each country or even each region has its own center with experts working on their river, which they know quite well. But two arguments for that. One is we try to look a little bit further into future. So our forecast with our system, with our approach, that's a probabilistic forecast that tries to look 5 to 10 days in advance to detect floods 5 to 10 days before they occur. And on the other side, we try to give a coherent overview of every flood in Europe, ongoing floods and forecasted floods all across Europe, which is also useful for improving correlation and coordination of international help. We have the same symbols and pictograms for the Ebro as well for the Tisza, a tributary to the Danube. So that's easier to see what's happening in Europe on a whole thing. This picture is a picture of a screenshot of our web interface for EFAS. Since 2011, now we are operational under the GMES, the Global Monitoring for Environmental and Security. So since 2011, we are also going global. That's a joint cooperation between the European Commission Joint Research Center, that's the organization I work for, and the European Center for Medium-Range Weather Forecasts. The aims are almost the same as for EFAS. Maybe here we are trying also to provide added value to existing systems, but there might be regions without any other information at all. So that's the first information or the only information they might get for this one. Our targeted users for this one are national hydrological services, river commissions, international protection and disaster response organizations. We already have cooperations with the newly founded Brazilian Flood Forecasting Center and also with the Mekong River Commission. So, how we do it? That's we put two computer models, two numerical models together. One is from ECMWF and one is from us. These computer models simply try to, not simply, but they try to migrate natural processes like snow, glaciers, influence of vegetation, influence of soil into our computers and to evaluate and to model floods in the end. So from rainfall to stream flow in the end. In the end, we put in weather forecasts. Not local one, but a global weather forecast, which comes also from ECMWF, into our model, and we get out maps of stream flow. Then we try to make it a little bit more obvious to show what's happening there. We put in pictograms for rising floods, for declining floods. We also put for every point you can, or every flood point, you can have a point information. The difference to other models is that we are probabilistic, that we don't put only one weather forecast into our model, but we put in ensemble forecasts. So instead of putting one, in this case, we put in 51 different forecasts for the same day into our model, and we get also 51 different outputs of our model. Now that's this slide, and if we give this information to decision maker, they will tell us, okay, what's this? We call it also spaghetti plot because you can't see so much, or you see too much in the end. So we've tried to find a way, or we found already, or we are on the way to find every time a better way to make this more obvious, to make this more fitting to the needs of decision makers. But in the end, it will stay a probabilistic forecast, and you have to scope with this one, or you have to adjust to this kind of matter. That's not a simply deterministic forecast which tells you tomorrow there will be a flood with this level, fine, everything is great. No, that one is you have 50% of flood next day, maybe. So, two examples for this one. The first one is a South Asian flood last September, October. You may have still the pictures of a flooded Bangkok in your mind. Here we tried, or we forecasted 5 to 10 days in advance the flooding for the Mekong River and for the Chao Phraya, which is the river which flooded Bangkok as well. And our forecast fit quite well because it was really in the case that plus minus 1 day, this flood was really occurring. The other example is a recent one, last month, Australia. Australia for sure has its own flood forecasting system, but here we can really show or look at the results and compare them immediately to what really happens. That's the advantage of Australia. And also we have some cooperation with Australian Bureau of Meteorology. Here we forecasted a flood for the city Wagga Wagga in South Wales, and 5 to 7 days in advance. And after that, we looked for if our floods forecast was accurate, and we found out, okay, that was a major flood in this region. So for summing up things, we have set up this global flood awareness system already since July 2011. It's operationally. We can demonstrate its feasibility. We have some existing collaborations. We try to get more and to make this system adapt to specific river basins. And also we foster a global network on flood detection and forecasting. So get a network together to speak different people speak together about their experience about floods as well from a flood forecaster point of view. We have all these web interface and all these things, but we still have to work really heavily on the stuff internal to make better predictions and to verify our results now. That's still a huge work forward we have to do. Thank you for your attention.
Thank you very much for your presentations. We have some time for questions, if anyone wishes to ask.
Liz Gallagher from Environmental Research Web. I have a question for either of you, which is how much can you do once you know 5 to 7 days in advance about a flood? What can you do to mitigate?
That's maybe my part. What we do is we warn the hydrological centers and we warn the national organizations and the international organizations. We don't go really public because that's part of each national organization. And they are working for disaster management, and we don't want to interfere their work with a different forecast they send out. So we warn the warning, that's our part. We warn the warning centers.
Jonathan Tyrone with Bloomberg. In the last few years on the Danube, we've seen heavy flooding, and this year we also saw severe drought, and that was, in terms of decision-making, impacted shipping and transport and logistics throughout Europe. How much of a reach would it be for you to use your data to also forecast drought scenarios? I mean, if you're looking at watersheds and rainfall or absence of rainfall, can you extend these models to include drought?
That's an ongoing task already. We have several discussions, several groups up there for discussing seasonal forecasts. At the moment, we put in medium-term weather forecast in. In the end, that's mainly a part of forecasting the meteorological conditions. What we do is the uncertainty of a forecast gets really worse if you go longer in time. So if the lag time is longer, it gets worse. For the next day, we know maybe for sure, okay, tomorrow it will be sunny or almost the same weather as today. But next week, quite unsure. And in 2 months, no clue. There could be a flood or nothing. So a single flood, a single big rain event can destroy the whole forecasting settings of our drought system for the Danube. So we're still going in this direction, but the uncertainty of these systems for drought prediction is quite high.
Yeah. If I can add something, and then forecasting is only one of the options, say, to reduce the potential impacts of floods as well as droughts. There is a general consensus on the fact that we should invest more and more in prevention measures, try to plan land use as well as urbanization in a way so that we are more resilient to hydrological extremes, both floods and droughts. And yeah, to have a strong forecasting system is just one of the many steps required to deal with growing flood risk or growing drought risk.
Other questions? No? Okay. Thank you very much for your presentations. We'll finish here. You're welcome to approach our speakers after the conference. And if you give me your slides, I can upload them online to the media website so that they have access to it. The next press conference is at 2:15, and it's on reducing greenhouse gas emissions, renewable energy, and CO2 storage. I hope to see you there. Thank you.